Thank you, everyone. It's a pleasure to be here in beautiful Vienna, so thank you so much for having me. So, like I said, my name is Predrag. You probably most likely know me as the maintainer of cargo-semver-checks, which is a linter for semantic versioning in Rust. The idea is that it helps us all prevent accidental breaking changes, which frustrate everyone, both developers and maintainers alike. And I also maintain and authored the Trustfall query engine that cargo-semver-checks is built on top of. I also write a blog that has everything from introductory articles on Rust's functionality, such as sealed traits, all the way to horrifying ways that you can cause accidental breaking changes in Rust by doing something as naive and benign as adding a private import statement. So if that sounds interesting, please go ahead and check this out. But this talk is about testing. So why is testing important? Well, the art of software engineering is about two things. The first is that we'd like to produce correct code that our users can depend on. And second, we want to spend as little time as possible on testing. Now, what do I mean by this? I mean at least two things. One is that tests should not take a very long time to run, but also that our act of adding and maintaining testing by itself should not consume a large fraction of our time. This turns out to be quite difficult in practice, and that's what this talk is about. Now, Rust has a wealth of testing functionality already built into the language. We have everything from unit tests to a very helpful linter called Clippy that I'm sure everyone here has already used. We have doc tests, which ensure that any examples that we have in our documentation for our library actually work and behave as expected. And we have the ability to write end-to-end integration tests, which consume our libraries as if they're an external user as opposed to testing the library from inside. This talk is not about any of these techniques. There are plenty of resources about them. The Rust book is fantastic, so please go check that out. This talk is about three more advanced techniques: invariant testing, snapshot testing, and deterministic simulation. And throughout this talk, I will be giving real-world examples of using these three techniques in cargo-semver-checks and in Trustfall. And in fact, these two tools would absolutely not be possible without these three techniques, and especially not as a essentially one maintainer open source project. So that's something that I would hope that everyone can keep in mind for the rest of this talk. So let's dive right in. Let's talk about invariant testing. The idea here is that we want to proactively make sure that the data that we're working with looks right, for some definition of looks right that is appropriate for our program. Let's take a very simple example. This is a binary search implementation. This is an algorithm I'm sure everyone here should be probably familiar with. We have a slice of integers, and we're looking for a particular integer in that slice. We assume as a precondition that this slice of data is sorted, and we're just going to keep checking the midpoint of this slice until we either find that this element exists at some index or return none and give up. Now, this has a bit of a problem. That precondition is not actually checked or enforced by anything here. So breaking the precondition is a bug, but it's not just a bug, it's actually a silent bug. It's unfortunate because breaking the precondition will not blow up our code and cause a panic, and instead what we're going to get is garbage in, garbage out. So we had one problem, which is that the precondition is violated, and now we have two problems. The precondition was violated, the data isn't sorted, and also this function returned something that we didn't necessarily expect. That makes debugging difficult. So one thing that we could do is we could add this assert statement in the middle of our binary search that says data is sorted or else panic. Great. Small problem, though. This is a check that always runs. The point of binary search is that we should be able to find the element we're looking for in log n time. Now our entire function is O of n always, including in production. Now, for production-sized values of n and log n are very different numbers, so obviously this is not going to cut it. One thing that we can do to make this better, though, is we can make this assertion only happen in debug mode by switching assert to debug assert. And that already makes stuff a lot better. Now, this is only something that is checked in debug builds when we run cargo run or cargo test. As soon as we specify -- release, this assertion is not checked, it's elided. And the mechanism for doing this is actually quite interesting. If you haven't looked into the guts of debug assert, this is how it works. It's equivalent to this CFG check against this debug assertions name, And if that happens to be true, then it just turns into a regular assert that we had before. Now that CFG command is interesting. It's actually allowing us to do conditional compilation. What that means is that we get to specify by CLI flag passed to rustc whether we want that condition to be true or to be false. If it's true, it's an assert. If it's false, this entire statement ends up being if false, and then rustc deletes the whole thing as if it was never there. So great. We used debug assert. We kept prod fast. Our code is better than before. Our test suite will catch unsorted slices. We're good, right? Well, as it turns out, we can do even better than this. And the way that we're going to do better is by observing that we actually have an interesting invariant inside this loop. An invariant is a property that is always true. It is always true if the precondition is kept that the left boundary of our indices and the right boundary, so right -1 because our right boundary is exclusive, are always on either side of this midpoint index. That is just how math works. And if the array is sorted, then the data at those indices is also ordered in the same way. So data of left is less than or equal to data at mid, and data at mid is less than or equal to data at right -1. And if this isn't true, then our precondition has been violated. So here, we're checking something slightly different than what we set out to check initially. This is not necessarily as strong of a check, but it's still a check that will find if the slice is unsorted in a way that mattered to us, that would have caused that unfortunate unspecified behavior to happen. This is also a lot nicer, though, because this is a much cheaper invariant. That loop only goes around log n times, and we only check 2 things inside each loop iteration. So now, we're essentially getting to have our cake and eat it too. Our check is only log of n, but we're still asserting that this precondition holds to the extent that we care about it. This is the point of invariant testing. Now, the way that this works in practice has to be a little bit customized to the specific use case. In cargo-semver-checks, for example, we have an invariant that if you didn't check anything in the API, there shouldn't be any breaking changes. That seems reasonable, right? You didn't change anything. And the best way that we know how to simulate not changing anything is just testing a package against itself. If we test it against itself and cargo-semver-checks reports a breaking change, we know that to be false. We know that to be a false positive, that's a bug, and so we're not going to let that pull request merge. This is a way that invariant testing helps us in the real world. In the Trustfall query engine, we also have some invariants. One of them is that when we look at the results that our query produced, the number of output columns in the query has to match the number of outputs that were selected for output. Otherwise, something either came out of nowhere or we forgot to output something. Either way, whichever way this mismatch goes, something is wrong, and we need to bail and inform the programmer that something has gone horribly wrong that we need to take a look at. So the point of invariant testing is that we want to get more value out of each test. We want to be extra sure that everything has gone as expected. And what this has as a downstream effect is that it means we catch more bugs earlier. And that means we spend less time debugging. This is something that's very, very nice. So with invariant testing out of the way, let's dive into snapshot testing. The idea behind snapshot testing is that any change in behavior in our program might be a bug. It might not be, but it might be a bug. And so we want to review all of them just to be sure. Here's a code example that we'll use to demonstrate this. Here we have this split words function. All it does is it just takes a string, splits on white space, and returns a vector of all of the words. And we've written a unit test. For the input hello world, running this function should return a vector with hello and world as separate items in the vector. Not that complicated. The way that this test works is we have this expected output, and then we actually run the function, compute what the output is, and then we assert that running the function produced the output that we expected. This is not rocket science. But one thing that is interesting to notice is that we wrote this expected value by hand. And in this case, that is totally fine. This is a very simple function, no problem there. Imagine if this function, though, was the optimizer of a database engine or the parser for a programming language. All of a sudden, this expected output type is a lot more complicated than a vector with some strings inside. And so writing that expected value is suddenly a lot more complicated, too. It's not as easy to write that. But wouldn't it be nice if we could still write some test that looks vaguely like this? That's the idea of snapshot testing. So instead of writing an output by hand, what we're going to do is produce a pair of files that we're going to read from disk, and they're going to be a matched pair where we load the input, we load the expected output, and then we want to make sure that everything checks out. So the output here is generated by running the function and not handwritten. This is a substantial deviation from how we were doing stuff before, but at the end of the day, everything is still the same. We still run the function on the input, and then we check whether we got the output that we expected, except the output now is a snapshot as opposed to something that we hand wrote. So it's not that different from regular unit testing. But because we don't need to write the outputs manually anymore, all of a sudden it's much, much cheaper to produce these kinds of tests en masse. So the best thing to do here is at every boundary between different components in your system, just snapshot everything. That's super, super nice. It means that the snapshots are now saved in the repo. They're part of your regular development process. Changes to them are visible in pull requests. And what that means is that that is something that you can also review during your regular code review process. Now, there are also some practical considerations to make the best possible use of this. An obvious one is that it's nice if your types, both for input and output, are easily serializable. The serde library is fantastic for this, and it's usually as simple as just slapping a derive on that. But having serde in our public API is not necessarily always the best idea, and so we might want to avoid having it in our public API by defining a conditional derive. So we can use this config-attr attribute to say that only in test configurations should our types be serialized and deserialized. That means that serde is now a dev-only dependency if we want it to be, and our types are not unnecessarily with a bigger public API than we intended them to have. Another thing that you'll quickly notice if you start using snapshot testing is just how much code that we rely on is highly non-deterministic. And that is very unfortunate. Hash table iteration order is randomized. That is something that has probably bitten more than one of us here in this room today. And so you will frequently find that if you care about iteration order in your outputs, it might be better to switch to B trees as opposed to hash tables. And another non-determinism source is if you use absolute paths, then those absolute paths are different on everyone's computer, including on CI, so probably don't stick absolute file paths in your snapshots. All of this is something that you can discover on your own way and implement yourself in your own snapshot testing library, but I would encourage you to not actually do that unnecessarily. Instead, check out the Insta library. It comes with batteries included. It will help you do all of this stuff out of the box. And while there are some cases where you might need something in addition to what Insta offers, Insta is really, really good for the 99.9 percentile of cases. In the real world, snapshot testing is also very useful. Cargo-semver-checks uses it in several places. For example, let's say that we are tweaking one lint that attempts to catch one style of breaking change, and we notice while running the tests that the outputs for a completely different lint have changed. This is always a bug. Tweaking the logic for one lint should not affect any other lint in the system. This is something that is very, very easy to notice when everything is snapshotted because the snapshot files have changed. Another example is when implementing a new lint, we write some example code just to make sure that the lint catches the stuff that we intended it to catch. But every so often we find that the same example code actually triggers another lint as well. Is this a bug? I don't know. Sometimes it is, sometimes it isn't. And snapshot testing just allows us to have a point in the development process to have this conversation. Did we expect this to happen? Is this a problem? The answer is sometimes yes, sometimes no, and we will make that judgment on a case-by-case basis. So the key idea here is that at the end of the day, bugs cannot sneak into existing code without being detected, because a bug, in order for it to be a problem, will change behavior, and that change in behavior is something that we now have the opportunity to catch. Because any change in behavior might be a bug, we will review them all just in case. And I can't stress this last part enough. The reviews are the point. If you're not reviewing the changes to your snapshot files, you're not actually testing. You're just pretending to test. So please make sure to review all changes that happen to your snapshot files. That is the key point for using this technique effectively. Great. That's 2 of our 3 techniques out of the way. Let's talk about the most fun one, deterministic simulation. Now, I'm sure most of us have written end-to-end integration tests at some point in our lives, and I'm sure that most of us have arrived at the same reasons for hating that experience. The most common reason is that end-to-end integration tests just take forever to run. If they finish in minutes, consider yourself lucky. I have a friend whose integration test suite takes tens of hours on a build farm. Not the most elegant experience. The second problem is perhaps even worse, though. Integration tests are often flaky and not reproducible. And this leads to a really terrible development experience. We end up with situations where, OK, did the tests fail? Well, maybe something flaked out. Just try running them again and see if that fixes the problem. This does not exactly inspire confidence that everything is OK in our code base. But the problems go much deeper than that. This is what the process of debugging one of those test failures looks like. We have some input way to the left, we have some expected results way to the right, and we have some big black box of end-to-end processing in the middle. And now our test has failed. It says we didn't get the results that we expected to have. Oops, there's a bug. Where, though? It's somewhere in the middle. OK, well, maybe we read the logs very carefully, and we have a hypothesis that it's a particular component that's the problem. So we grab the test case off of the integration suite that we were running on our build farm, and we try to reproduce this locally. We maybe have a hypothesis where it is, so we add some extra logging around there. So now I rerun this end-to-end test locally, and that takes a while. So we wait, and we grab a cup of coffee, and maybe go out to lunch, and then come back, and all of the tests passed. Darn. Well, what now? This is something that's happened to me multiple times, which is why I love deterministic simulation testing. We can do way, way better than this. Don't take my word for it, though. Tiger Beetle is a database. It's a database that uses deterministic simulation testing. And just a few weeks ago, they found the sort of perfect storm of an unfortunate bug. In order for the bad thing they detected to happen, they needed to have everything go wrong in precisely the correct order. They needed to have multiple failovers happening at the same time, with disks delaying writes, with nodes crashing, and everything has to happen in exactly the correct order. And once they found this bug, they're able to reliably reproduce this bug in less than a second. Not bad. Just check out the repo, check in this scenario, check in this magic number seed that you get, and this bug will never, ever happen again because it costs you 1 second to make sure that it's never, ever there. That sounds lovely. And if I may flex for just a little bit, the Trustfall test suite also works this way. We run hundreds and hundreds of very complicated end-to-end query tests, and on my 3.5-year-old laptop, our entire test suite finishes in 1/3 of a second. Again, development is very nice when you have stuff like this. So let's talk about how all of this works. The key observation here is that in a fully deterministic world, our bugs either always happen or they never do. So what we're going to do is we're going to treat non-determinism as a bug in and of itself, and then eradicate it in every way that we can. This also means that, by definition, if everything is deterministic, flaky tests are impossible. They just can't happen, because that requires non-determinism, and we will root out all sources of non-determinism as a bug. Here's how this works. Instead of having this big, non-deterministic, monolithic mess that is impossible to test in a reasonable way, we're going to split up our programs into 2 different sections. One that encodes our very complex but fully deterministic logic. So this would be something like, let's say, a state machine. And it might be very complicated, but it's fully deterministic. And then we're going to take all of the non-determinism in our program and just shove it in a box and call that the simulator. This is what it looks like in Rust. We're going to define the simulator trait, and it's going to do everything that is required for a program to work that might be non-deterministic. If you're not sure, just shove it in the simulator. So reading from files, maybe non-deterministic, stick it in the simulator. Sending packets over the network, non-deterministic, stick it in the simulator, and so on. And then we're going to encode our very complicated business logic in this type that takes the simulator as a parameter. So we're going to use dependency injection to say, here's how you interact with the outside world that might not be as this pretty deterministic setup that we all know and love. So our code is completely isolated from all non-determinism except what is passed in by the simulator. And then we're going to define 2 or more implementations of this simulator trait. Some of them are going to be used for testing, and some of them are going to be the real-world implementations that actually read from files and send packets over the network and so on. Now, our test simulators can do all sorts of different things. They could randomly choose to introduce failures in ways that we control by a random seed, or maybe we have a scenario set up that says, drop all packets after the first 3. All up to you, you can pick. And the real-world simulator, since it actually interacts with the real world as a program would expect, it still has some surface area that we have to test. But since we put all of the really complicated logic somewhere else, the surface area here is much smaller and easier. So it's just read from a file or send a packet to the network and not something much, much more complicated than that. So it's a smaller state space. It's easier to test. It's easiest to explain how all of this works in the real world through a real-world example. The Trustfall query engine relies heavily on deterministic simulation testing. So here's that diagram from before. We have an input query string on one side, and we have results on the other. And we're evaluating this complicated query everywhere in the middle. But that is not a monolithic process. It's actually broken up into several different stages. First, we have to parse the query. Then we have to make sure that it type checks against the schema. We create a query plan, and then we actually run it. So great. Snapshot testing is cheap. Stick a snapshot at every boundary between all of these different interfaces. But since we now have snapshots, something very interesting can happen. We can actually reorder how we run all of these tests. So instead of running everything back-to-back sequentially, we can run everything concurrently and in parallel. Here, each output snapshot of one stage is the input snapshot to the next stage. And in this case, we're already getting performance benefits, because instead of running everything in a single-threaded linear fashion, we can run all of this in parallel on many cores concurrently. This is already awesome. My test suite is already faster, but we're just getting warmed up here. Because we're simulating the network and disk and all of the sources of non-determinism, we're not actually bottlenecked by hardware anymore. Reading from the network, in quotes, is free because we're just reading some bytes out of memory. Reading from files, again, free, because we've already deserialized those bytes in advance in the test scenario, and so again, it's free. We're not bottlenecked on the hardware actually doing its job. So we're not just faster because of parallelism, we're no longer dependent on our hardware to be fast. You don't need a faster hard drive to run database tests, and that's really lovely. For the rest of this, let's take a look at the reasons to hate integration testing. So I already mentioned that we can love deterministic simulation because everything is nearly instantaneous as opposed to taking forever. But we're just getting started. Not only are these tests much faster to run, by their very existence, they're actually much stronger than a regular end-to-end test suite. And to convince you of this, I want to walk you through an example. Let's say that we have a bug. We run all of our tests, and at some point, one of the snapshots just doesn't match. It's buggy. And let's say that it happens in this query planning stage. First of all, we located the bug immediately, because that specific test failed, nothing else. So we immediately know where to look. And this bug doesn't go away on rerun, because everything is fully deterministic. So we can run cargo test as many times as we want, and we will always, always trigger the same problem. So this is very, very easy to drill into and figure out what went wrong. But because every other stage of our tests still runs on these deterministic snapshots, we know that nothing else is the problem. The bug is highly localized in this one specific stage. Because everything else runs off of the correct snapshots that we already had in our code base, we know that the bug's impact is bounded. So we only need to look at the query plan generation stage and nothing else. So not only is deterministic simulation giving us a massive amount of performance, it means that our tests are incredibly reproducible and easy to work with. But adding new test cases is also a breeze. Let me show you. This is an exact replica of what the process for adding a new test case in the Trustfall codebase looks like. We might have a tricky new test case that we will encode as a query and some arguments to run. And we have a script called create valid query data. This script creates all of the snapshots that we need in the case where nothing fails. We run that script, it produces some output, and it's done in about a quarter of a second. And then we run git status to figure out what happened. Oh, look, a whole bunch new snapshot files, because we generated them by running the actual engine and dumping all of the intermediate states to disk. Now we have a bunch of new deterministic snapshots that are good to go. Great. add them, commit them, open a pull request, and go ahead and merge it. If everything looks fine in all of these snapshots, that's it. It's a really simple process. So it literally takes longer to think of what query should I be testing than to write the test cases to test end-to-end and all of the stages in between. And to close out, I want to take us back to the goals of software engineering. We want to produce correct code while spending as little time on tests as possible. I want to convince you that these two things are not actually at odds. They can feed into each other and form a virtuous cycle. Because when we produce correct code with techniques like Snapshot, Invariant testing, and deterministic simulation, our tests are very easy to run, they're very fast, they're deterministic, and so we don't spend a lot of time debugging. That means that we spend more time producing correct code. But because we now spend less time debugging and more time producing correct code, it means that also as a fraction of the total time in our development cycle, debugging takes less and less time. And the more snapshots we have, the better we are at finding all of these bugs. The better we are at ensuring determinism in everything, the more likely it is that we will find all the accidental cases of non-determinism that might sneak into a repository. So the better we get at writing correct code, the more test coverage we have. The better our test coverage, the better we are at writing correct code. That is how all of these projects can grow. So investing in really good test infrastructure is extremely worth it. It's the most valuable thing that you can do in the first couple of weeks that you start a new project. By this point, I hope I've convinced you of a few things. One is that better tests let you build bigger in less time. It takes some amount of time to set this up, and you will immediately recoup that the first time you don't have to debug some complicated, long-running, flaky, end-to-end integration test. If you proactively ensure that your invariants hold with invariant testing, if you snapshot everything and carefully review your snapshots, and if you use deterministic simulation to turn end-to-end testing into a joy, then your programs will be better off, you will be happier because debugging sucks, and your users will love you for the amount of fantastic new functionality that you can ship with all of the time that you're no longer wasting on debugging. And if I might throw out a fourth suggestion here, if you maintain libraries that other people use, please consider avoiding breaking semantic versioning unnecessarily. You can use the cargo-semver-checks tool that I maintain, and if that work is something that you'd like to support, please consider sponsoring me on GitHub Sponsors. If you'd like to learn more about Trustfall or cargo-semver-checks, there's actually a couple of Impl Room projects that are around contributing to these projects. So please find me around the conference or go to the Impl Rooms, and I'd be very happy to help you get started. And with that, thank you so much for your time and attention, and I'd be happy to talk more in the Q&A.